Hey everyone, this is Mr. Z. I am going to go through part 2 of our final exam, which will be questions 10 through 20. So let me get to question 10 here on the final review. Matter. We're going to be starting with matter here. So consider the four containers below. So we have container A, B, C, and D here, which contain a mixture. So as a review, a mixture is going to have different types of particles here. So let's start with A. Take a look at this. Every single shape here, I should say, every single particle is exactly the same. So we have one kind of gray and then two white coming off of it. All of them look the same. So it is not A. A is not a mixture. B, this particle and this particle are different, and this particle is different. They're all different. So that is going to be B is a mixture. If we look at C, these are all the same, so it is not C. If we look at D, here's that shaded in circle with two white ones off the side, but then this one's a little bit different here. And these two are the same, but we do have some different ones. So D is also a mixture. Make a better D there. Okay, so now B, which contains a pure substance. Let me do some erasing here so we can see everything. So a pure substance means that every particle is the same. Every particle is the same. So when we take a look here, this is pure because they're all the same. B, it's basically going to be everything that's not a mixture is going to be pure. Pure is, or I should say, mixtures are impure. Pure would be a compound or an element. So A is going to be pure. C is going to be pure. But B and D are not pure. C, which contain only one type of compound. So a compound is when we have two or more atoms that are bonded together, and we know that things are bonded together when they're touching. So here, this is pure. They're all the same. And we have different types of atoms that are bonded together. We have a shaded one, and that's a little bit different than the unshaded ones. So A is going to only have one type of compound. B, here's a compound, but it has other stuff in there, so it's not only one type of compound. C, this is not a compound because both little circles are exactly the same, as far as I can tell. They're both unshaded, they're both the same size, and so we only have one type of atom, even though they're bonded together. And then here we have two different types of compounds. So we have a compound here that we saw in A, and we have a new compound here. So there's two different types of compounds, so it's not only one type of compound. So that's not satisfied. We can't put D down for part C. So then part D, which contain only one type of element. So an element is just a single shape. All right. So C is only going to contain one type of element because everything is exactly the same. Every little ball here is the same as far as size, same shape. They're both unshaded, same color. Everything is the same about them. So C would be just one type of element. All right, so we got B, D, A, C, A, and C. Okay, let's scroll down to 11. Whoa. I gotta click this. Let's see, can I just do this? Here we go. All right, same thing, same type of question. We got a little bit more here. We talk about solids, liquids, and gases. All right, so let's quickly review solids, liquids, and gases. Solids, particles are really compact to each other. They're only going to have a little bit of space to just vibrate back and forth. Liquids are going to have a little space in between them in which the particles can slide past each other. And then gases are going to have a lot of space between them because those particles are moving in all random directions. All right, so first, let's do mixture. All right. It is somewhat tough to tell. I would say C is a mixture for sure. And I'm going to call B a mixture also. So B and C. The reason I'm going to call B a mixture, it's kind of tough to tell, but it looks to me like we have this particle where we have a dark circle and a light circle connected, but some of them don't have a light circle connected to them. So if we look at this one right here, that one just looks like a dark circle. There's no light circle connected to it. If we look at these two right here, there's one light circle in between them, so only one of them can have it, and the other one must just be a dark circle. So I'm going to say that there are two different things there, which would make it a mixture. All right, so now which contains a pure substance? Remember, pure substance, every particle has to be the same. So I would say A, and the reason that's pure is because I think we have a very dark shaded in circle and then a lighter shaded in circle. And we just have that repeating over and over and over and over and over again. And so all we have is this particle. We just have a lot of them all connected. So I would say that that is pure. B is not pure because that's a mixture. C is not pure because that's a mixture. And then D, I would say that is pure also because everything in there is the same. C, which contain only one type of compound. Okay, so a compound, remember, is two or more. They're different shapes, or maybe they're the same shape but different colors, but two things that are different. They have to be bonded to each other, and only one type here. So I'm going to go with A on that one because we have this. B, remember, we have two different types of compounds. We have big, shaded, little circle, and then just a big shaded. So those are two different things. Even though they contain the same thing, they are different. They're not exactly the same. C, we got a couple things going on there. So it's not only one type of compound, it's two different types of compounds. And then D, I wouldn't call that a compound because they're all of them are exactly the same. So I would call D an element because everything is exactly the same. So then solid, I would say A and D are solids because they're very compact. They don't seem like they have a whole lot of space. Which contains a liquid, I would call that B because there's a little bit of space in there. They could slide past each other. And then a gas, I would say, is C because there's a lot of space in there. So CB, AD, A, then D, then AD, then B, and C for our answers here for number 11. Okay, so now 12, same type of question. So what I'm going to do, I'm going to ask you to pause the video, see if you can answer these on your own, and then unpause the video and see if I got them correct. Because if you're just going to copy down everything that I say, that's probably not going to get you super ready for the exam here next week. So try to do some of these on your own. And any of them that you get confused with, you can rewind the video and watch me explain it between 10 and 11 and see if that helps. All right, so pause the video. All right, welcome back. All right, here we go. Let's see how you did. Okay, which contains a mixture? Which contains a mixture? I would say, this is a tough one. I would say in this case that none of them contain a mixture. None of them contain a mixture. I'll just put like an X there. All right, so you can put an X in there. None of them contain a mixture because A, this, and this, they're all the same. B, although it's a similar picture above, it looks to me like every single one is a shaded and an unshaded circle. I don't think it's the exact same picture. It looks similar, but it looks like every single shaded ball has an unshaded ball connected to it. And it looks to me like they might have a little bit more space. It might be a little bit easier to see. C, this is the same, this is the same, this is the same. And then D, they all look the same. So I would say none of them are a mixture. Which contain a pure substance? Well, that would be all of them then. So that would be A, B, C, and D. They're all pure because every single particle in the picture is the same. And then which contain only one type of compound? Okay, so a compound, remember a compound is two different shapes, or it could be two different colors or sizes, or there has to be two or more things that are different, but they must all be connected. And then everything else must have the same type of connection or the same particle in each one. All right, so A, everything is exactly the same. So that is not a compound. That would be an element. So I could do part D here already. So this is a element. B is a compound. It only has one type of compound, a big shaded and then a small unshaded. C, I would say, is a compound because we got that one dark one in the middle, and then we got three light ones going around the outside, and they're all the same. And then D, I would say, is an element because they all look exactly the same. All right, which one is a solid, liquid, and gas? Okay, solid, D, not a whole lot of space there for those particles to move. They're just going to vibrate. Liquid, I would say B. They have a little bit more space to kind of move around, slide past each other. And then G, I would say A and C. So really, the solid, liquid, and gas has nothing to do with what the actual particles look like. Solid, liquid, and gas you can only determine in a picture based on how they're arranged. These are tightly packed. These are spread out. These have a little bit of room in there. All right, so solid, liquid, and gas really is how they're arranged. Element, compound, and mixture is really what they're made of. All right, so then 13, 14, and 15. 13 solids have a blank shape. All right, so there's a couple terms we could use here. We could say definite, which also means constant, which also means unchanging. Okay. The other we have is an indefinite. These are just the opposite. An indefinite, you could say variable, or you could say changing. All three of these and all three of these, so these three mean the same thing, and these three mean the same thing. So you can pick whatever you want. I usually do changing and unchanging. You can totally do definite and indefinite. All right, but solids have a what type of shape? Their shape does not change unless you add some energy into the system. All right, but if you have a solid and you just leave it in a environment that is the same temperature as the object, it just sits there. So an ice cube in a place where it's cold, or if you had a wooden block in a place that has the temperature of the block, all right, it's not going to change. So I would say that this is unchanging, an unchanging shape. And what about its volume? How much space does it take up? That doesn't change either. You can't squash a solid without putting some energy into the system here. So solids have an unchanging shape and an unchanging volume. All right, liquids, their shape changes constantly. We never know what shape a liquid is going to be. It really depends on what container it's in. So I'm going to use a different term here. I'm going to write indefinite, just so you can see. An indefinite. Oh, I spelled that wrong. Let me try that again. Indefinite shape, or you could put a changing shape, or you could put a variable shape. So the shape constantly changes, but its volume pretty much stays the same. So if I have 15 milliliters of, let's say, water, since it's a liquid in a graduated cylinder, and I pour that in a bowl, it doesn't take up any more or less space. It might change its shape and spread out more, or it might get more kind of like vertical, like in a graduated cylinder, but it's not going to take up any more space. So this is a unchanging, or I'll use the term definite. So you could put definite, constant, or unchanging volume for a liquid. Now, gases are kind of the funky one here. Gases have a changing shape. Those gases can be any shape, depends on what container they're in. And their volume can also change. You can take a gas and you can squash it together, or you can spread it out more. All right, so I use the example of a fog machine. You take a fog machine and you put some fog in, like a cup, in a coffee cup. You trap it in a cup. okay, and then you take it into a room and you let it out, it's going to spread out amongst the entire room and it's going to get stretched out so thin that you'll be able to actually see through it. It won't be foggy anymore. All right, so gases have a changing shape. Again, you could say variable or indefinite, and I'll put variable volume. So I could use any of those words. I just used a bunch of different ones just so you could see. So it could be unchanging, and then it could be changing and unchanging, and then it could be changing and changing. You could just use the word change and unchanging in each of them. You could use constant, variable, or definite. It doesn't really matter, just as long as you know that some things will change, some things will not change. All right, let's go on to now gas laws. All right, so first one, calculate. So here's how I always set it up. All right, I'm going to have my PV, NT, all those type of things off to the left-hand side as I read. So calculate the final pressure. Okay, that's a keyword. So I'm going to put pressure, and it says final. So I'm going to put P2 equals question mark of a cylinder if the car engine original volume. Okay, so P and V, that is Boyle's law. So P2 equals question mark. It says, let me erase that. Original volume. I'm going to put that all the way over here just to separate it because I want my original and I want my final stuff separate. So volume 1 equals 150 milliliters. All right. At a pressure, so now this is our initial pressure, is 1.8 atm. Okay, assume no change. Oh, whoops, I forgot this. Pressure. Okay, I'll circle this. All right, the final volume is 300 milliliters. Okay, so that's V2 is 300 milliliters. Now, it doesn't really matter. I have my ones over here and my twos over here. You could totally flip-flop that and put your ones on this side and your twos on this side. That would make it look more like the equation, all right? But now, okay, so we have this set up. All right, we are going to, because it's Boyle's law, this is the one funky one we're going to multiply same side, and we are going to divide by the third number, okay? So I can take this question mark times 300, but that's not going to help me simplify anything. So I'm going to do that over here. I'm going to do 150 times 1.8. Okay, and that's going to equal 270. So I have 270 over here. Let me move this. Okay, and then I'm going to divide by my one number over here. And that's going to get me 0.9 for my pressure. That's going to be my pressure. So I'm going to multiply same side, divide by the third number, and this is a pressure, and so the units are going to be ATM. Pressure is ATM. Volume would be milliliters or liters. We'll have, let me erase this here. We'll have temperature should be in Kelvin, and we should have N, which would be like number of molecules. Okay, and just to kind of help us recognize what we should write. All right, so we got 0.9. Now, just a quick check here. Boyle's law is the one indirect relationship, meaning one goes up. Oh, let me see. One goes up, one goes down. So here, I had my volume started at 150 and went up to 300. So volume went up, so my pressure should go down then. So I started at 1.8, and it did go down to 0.9. And so that's a good, just quick check. It did go down, so that's good. I probably did it correct. Sometimes if you double check that at the end, you'll find out that you multiplied when you were supposed to divide, or divide when you were supposed to multiply, and it won't follow that rule. So Boyle's law is always indirect. One goes up, one goes down. Okay, Charles' law, Gay-Lussac's law, and Avogadro's law, they're always direct, meaning they both go up or they both go down. All right, so now let's take a look at 17 here. Well, I can erase this here. All right, a 0.5 liter tank of oxygen. Okay, so this is a volume. So I'll put like volume, since it's liters as we see here, equals 5.0. And a pressure of 2 atm. So pressure equals 2 atm. And a room temperature. Oh, so now we got a temperature here too. 396. 396. Okay. What will the pressure be? Okay, so pressure equals, all right, if the oxygen is cooled to a temperature of 373. Okay, so we only have one volume. And so that must have been just extra information because we can't find anything because we only have one volume. We're not looking for a volume. We don't know what it means. So I'm going to kind of erase that here. And I'm going to rewrite everything here. So let me go back to the laws. We have pressure and temperature, which gives us Gay-Lussac's law, which is P over T. And then on the left, it's the ones. On the right, it's the twos. So I'm going to rewrite my information that way. Okay, so I am going to do pressure equals 2 atm here. And temperature equals 396 K. And I'm going to put my ones in there. And then I want the other side to look the same, except it should be twos. So I'm going to erase this and put P2, T2. And the temperature is 373 K. And we're looking for pressure too. Okay, so now all of the laws, except for Boyle's law, like the first one we did, it's going to be cross multiply here and divide by the third number. So I'm going to take 2, here's a cross, 2 times 373, 2 times 373. Okay, and then I'll put a multiplication there. I'm going to divide by this third number. So divide by 396. Okay, and I get, whoops, I didn't check it, pressure of 1.88, we'll say. All right, 1.88, and it's a pressure, so that means it's atm. And that is my final answer. Now let's just double check. Okay, so my temperature went down. I was at 396 and now I'm at 373. So my temperature went down. It's a direct relationship, so my pressure should also go down. Well, it was at 2 and now it's at 1.88. All right, checks out. All right, let's erase this again. So I can go down to question 18. 18. The temperature inside my fridge is about 277 K. Okay, so that's going to be a temperature. If I place a balloon in my fridge that initially has a temperature of 295, okay, so it was originally at 295, and then I'm going to put it in my fridge. So that's my T1, my T2, and it is a volume of 0.5 liters. What will the new volume be? So new volume, that's a question mark. This is my original. Okay, so I got volume and temperature. If I, whoopsies, gotta click this. If I scroll up, volume and temperature gives me Charles's law. That's V over T, so I am going to write out my problem so it looks like that. Okay, so V over T, these are going to be my ones. V over T, these are going to be my twos. I'm just going to copy the information down. So this is 0.5 liters. T1, I got to get this on the numbers here. There we go. T1 was 295 K. V2 is my question mark. T2 is the 277 K. And let me just erase this stuff here. Okay, Charles' law, cross multiply. and then divide by the third number here. So let's take a look. 0.5 times 277 divide by 295 gets us, whoops, that was 29. Let me do that again. Didn't register. I didn't click it right. Divided by 295. There we go. All right, 0.47. I'll round that to, and I'll do liters. Oops, let me move this. Liters. That should be our final answer. Just double check here. Our temperature here was high and it went low. So our temperature went down. So our volume should also go down. Our volume was 0.5 and now it's 0.47. So it did go down, not a whole lot, but it did go down. So that tells me that I probably did it correct. Okay. So now let me get rid of this. Let me clean this up a little bit. Can I make this bigger? A little bit, not a whole lot. Okay. Number 19. Okay, I'm going to ask you to do number 19 on your own. You can go ahead and do 20 on your own also. You can pause it and then come back and check to see if you completed it correctly. So go ahead and give it a try. One thing I will mention here, it does give you two temperatures. Use the Kelvin. All right, don't use the Celsius. Use the Kelvin for that one. That's my one hint. And then 19. I think you can do that one. All right, so try that one on your own. I don't think you need any hints for that one. Pause it and come back and check to see how you did. Welcome back. All right, so let's check this one here. Let's see what we have. 15,000 molecules in a volume of 30. Okay, so molecules, that's going to be my N. So we have N and volume. So N and volume, let's see how that equation is written out. V over N for Avogadro's law here, V over N. So that's how I'm going to write it. I'm going to get back down there, V over N. Okay, so V1, whoopsies, here we go. V1 equals 30 liters, N1 equals 15,000. I'll just abbreviate MOL for molecules, okay? Later, after realizing the cylinder was losing gas, the number of molecules had fallen to 5,000. So N2 equals 5,000. We don't know our V2. What would the new volume be? All right, so let me change colors here. Maybe make it pop a little bit more. Again, we need to cross multiply here. So 30 times 5,000 gives us 150,000. And now we need to divide that. Let me put the multiplication there. We always cross multiply unless it's Boyle's law. We need to divide that by 15,000. 15000. Got to be careful with your zeros here. All right, that would be 10. And that would be liters because its volume is liters here. So our answer should be 10 liters. Double check here. N goes down. It was at 15,000 and it goes down to 5,000. So that means that our volume should do the same thing. Our volume should go down. It was at 30. Now it's at 10. We probably did that one correct. So that was good work. Hopefully you crushed that one. Let's try 20 here. Let me scoot this down a little bit here. Clean that one up. All right. You and your family have gone on a lovely fall Wisconsin weekend. The temperature when you blew up the air mattress was warm at 295 K. So we have, this is a temperature equals 295. All right, during the night, the temperature dropped to 278. So this is a temperature. This is initial. This is final or after. You woke up and the mattress is much flatter. Oh, we don't even calculate here. Explain in terms of molecular behavior what happened. Okay, so include these terms. Collisions, speed, molecules, space the molecules take up. So we talked about this in the beginning of the gas laws. pressure for a molecule is the amount of collisions. The more that the particles collide, the more pressure they create. So in a tire, if you have a flat tire, you need to put more air in there, more particles, so they collide more often, and then they're going to take up more space and blow up that balloon. So when they collide, you're creating more pressure. And that's why when you check the pressure, it's going to be bigger the more particles you put in there. All right. And there's other things that can change how many times they collide, but pressure is collisions. Volume is the space that the gas takes up. So, like if you put more molecules in that tire, they're going to take up more space. So if you have more molecules, it's going to take up more space. Temperature is speed. Okay, so when we warm something up, a gas, when we warm up a gas, those particles are moving faster. They're moving much faster. The faster the particles move, the warmer they feel to us. So something that's cold, those particles are moving very slow. N is like the amount. So if we have more particles, all right, that's going to affect how much space they take up. It could affect how many collisions they have, depending on what other things stay the same. All right, so we need to explain what happened here. Let me change colors again here. So what happened? The temperature dropped. Okay, so we want to say something about the speed dropping. The speed of the molecules drop. Okay, let's talk about collisions. All right, so if the particles are colliding, if they move slower, they're going to end up colliding less. The less they collide, the slower they're moving, the less space they're taking up. So let's put that into a sentence now. All right, so let's start with temperature, since that's kind of the information that we are given. Okay, so we'll say, as the temp decreases. All right, I'll have to abbreviate a little bit here since I'm not typing. But as the temperature decreases, gas particles slow down, causing less collisions. Okay, so there are less collisions now because the particles are slowing down. Okay, so we used collisions and we used speed. Well, as the temperature goes down, gas particles slow down. So I guess we didn't really use the term speed. If you really wanted to, you could say the gas particles' speed decreased. So I'll box this and say speed decreased. That would get you to say the word speed, but really my focus is so that you know that they're slowing down or that their speed is slowing down. And so if you say slow down, I know that you know that. All right, so as the temperature decreased, the gas particles slow down, causing less collisions. Okay, so that's two things here, but it's not the last thing. So with, kind of took up the period there, with less speed, there, I'll use it here, and less collisions, the particles take up less space. The particles are going to take up less space now because they're not moving as fast and they're going to be colliding less. And so that's why the mattress seems like it deflated. It's not necessarily that there are less particles in there. That could be the case if there was a hole. All right, but if there is no hole in there and the same amount of particles, it can still seem a lot flatter just if it gets colder. I don't know if you are a sports fan, but if you've heard of Deflategate, all right, that is one argument that was used, that it was a cold temperature for that game. And so the gas particles inside the football took up less space, making them flatter, which they got so flat that it was actually illegal. Well, I should say that it was a different pressure before the game and during the game, which is illegal because the umpires have to check to make sure they're at a certain pressure. So real world example here. Okay, so that was 10 through 20. That was part 2. All right, hopefully you got everything that you need there. And then on Thursday or Friday, you'll go through part 3, which will be 21 through 30. Then you can submit, turn this in, and then you can use this on your final exam to help you crush that chemistry test. So hopefully that was helpful. If you need to rewatch this video or if you have any questions, you can always contact your teacher. So thanks.